Good morning, champs. In the last videos, we introduced the boundary layer and approximated the velocity profile. Now, we go one step deeper. We want to understand where the momentum thickness comes from and how it connects to the governing equations. So let's start from the boundary layer equation for steady, incompressible flow over a flat plate. The continuity equation is du over dx plus dv over dy equals 0. And the x momentum equation simplifies to rho times u du dx plus v du dy equals eta times d squared u over dy squared. Since the free stream velocity is constant, there is no pressure gradient. Now we integrate this equation from the wall, y equals 0, up to the edge of the boundary layer, y equals delta. On the right-hand side, we integrate the second derivative of velocity. This gives eta times du dy evaluated between 0 and delta. At the edge of the boundary layer, the velocity gradient is approximately 0. At the wall, the gradient is related to the wall shear stress. So the right-hand side becomes the wall shear stress tau W. Now let's look at the left-hand side. We rewrite the terms using product rules and the continuity equation. After some rearranging, the expression becomes a derivative in x of an integral. We obtain d over dx of the integral from 0 to delta of rho times u infinity minus u dy equals tau w. This is the integral momentum equation. Now we divide by rho u infinity squared. This motivates the definition of a new quantity, the momentum thickness. It is defined as delta 2 equals the integral from 0 to delta of u over u infinity times 1 minus u over u infinity dy. Using this definition, the integral equation becomes d delta 2 over dx equals tau w divided by rho u infinity squared. This is the von Kármán integral equation. It tells us that the growth of the boundary layer is directly caused by shear at the wall. This expression measures how much momentum is missing due to the boundary layer. Let's understand it physically. The term u over u infinity tells us how much fluid is actually moving. The term 1 minus u over u infinity tells us how much velocity is missing compared to the free stream. Multiplying both gives the local momentum deficit. Integrating across the boundary layer gives the total momentum loss. So the momentum thickness represents the thickness of a uniform layer moving at free stream velocity that would produce the same momentum loss as the rail boundary layer. In the next video, we will combine this equation with our polynomial velocity profile and solve for the boundary layer thickness along the plate.